Hello everyone, welcome to lecture 26 on the online course of Introduction to Microwave and Optical Metamaterials. Today's lecture will be discussing about split-ring resonators and why they play a very important role in metamaterial design. So, first we will talk about negligible optical magnetism in nature, and then we will look into split-ring resonators which allow you to have some considerable amount of permeability in this optical range, okay, or even in the microwave range, mainly in the optical range, okay. And then we will see the equivalent circuit of a split ring resonator and how split ring resonators can be designed at higher frequencies. So, let us discuss about negligible optical magnetism in nature. So, at optical frequency, it has been found that all natural materials typically exhibit different dielectric permittivity epsilon, okay, than in vacuum, right. We have also seen that noble metals often show negative permittivity below their plasma frequency. Now, when you talk about the magnetic response, talk about magnetic permeability mu in natural materials, it has been seen that it remains nearly equal to that of the free space in the optical range. That means, optical magnetism is largely absent in nature and materials do not show significant magnetic response at these frequencies, right. So, indeed, in the famous textbook by Landau and Lifshitz, there is a quite general statement on the reason why a magnetic resonance resulting from orbital current in atoms should be negligible at the optical frequencies, and consequently the magnetic permeability ceases to have any physical meaning at those frequencies, right. So, typically people disregard magnetic susceptibility in the optical frequency discussions, assuming that mu is 1. Now, optical magnetism is largely absent because light's magnetic field interacts very weakly with atoms compared to its electric field, right. So, the problem comes from the magnetic coupling, right, because the magnetic coupling is basically proportional to the Bohr magneton. So, you have mu b, which is equal to E h bar divided by 2 epsilon E c, okay. Now, mu bar is the natural unit to measure the magnetic moment of an electron, okay. E is the charge, h bar is the reduced Planck constant, okay. Me is the electron mass, and a naught here is basically the Bohr radius, right. So, the magnetic coupling is proportional to the Bohr magneton, okay, while the electric coupling is basically simply you can write it as E a naught, okay. So, now what happens, because there is a proportionality of this alpha, okay, the magnetic interaction basically includes this alpha, which is the fine structure constant, and this alpha value is small, it is 1 over 137, okay. So, because of that, it makes the effect of light on the magnetic permeability alpha square times weaker than that of the electric permittivity. So, you can now understand that why the magnetic permeability because of light is very weak, whereas the interaction in terms of electric field is much stronger. So, as a result, only the electric component of the light can effectively interact with the atoms in conventional materials. And however, it's not that the magnetic field is not playing any role. The magnetic field component of the light basically plays an auxiliary role or an indirect role through its relation with the electric field, which is governed by the Maxwell's equation we have all seen. So, the magnetic response, which is mainly due to the electronic spin states in naturally occurring materials, diminishes at frequencies which are higher than a few gigahertz. So, below that you can have some magnetic response, but after that beyond few gigahertz the magnetic response is very weak. Okay. Moreover, there are no free magnetic monopoles, and thus it is not feasible to obtain a magnetic plasma as we can obtain for electrons, right. So, it is indeed challenging issue to achieve any magnetic response in the microwave or higher frequencies, okay, let alone extreme values like negative permeability and all. So, you are not at all getting some simple response from the magnetic part of the electromagnetic field in these high frequencies. So, the metamaterials have basically revolutionized this possibility of achieving magnetism at optical frequencies. Okay. So, unlike natural materials, we all know that metamaterials are basically based on artificial subwavelength structures which are known as meta-atoms, and this meta-atoms basically allows the magnetic field of the light to interact more effectively with the meta-atom, and that can give rise to artificial magnetism. Okay. So, this interaction is not restricted to the atomic spin states which are typically ineffective at optical frequencies, right. So, in this particular discussion we will focus on a series of magnetic elements which are developed during the last few decades in the metamaterial research, including the split ring resonators, metallic staple arrays, okay, coupled nanorods, nanoplates, nanostrips. Okay. So, the magnetic response in this kind of structures ranges from say the microwave frequencies up to the entire visible spectrum. So, you can see that how exactly artificial magnetism can be made real using this kind of metamaterials. Now, in the pursuit of magnetically active structures at high frequencies, which is one of the core area of the metamaterial research, people have seen that split ring resonators are very important. So, why they are interesting? Because you can design a structure that can boost up the interaction of the elements with the light's magnetic field. So, in this regard, for the microwave range, a recipe was suggested by Sir John Pendry, where he predicted that a pair of concentric split ring resonators, okay, these are also called double split ring resonators with subwavelength dimension, and they are facing in the opposite direction, okay, they can give this kind of effect. So, this split ring resonators generate an effective permeability which is different from unity. That means, it is showing magnetic behavior or response at microwave frequencies. Now, the concept and the design of split ring resonator predates Pendry's work. Originally, it was described by Hardy in 1990s, but John Pendry's reinvention of SRR in the it's almost like close to year 2000, okay, 1999 or 2000. That is when he could lay the foundation of many magnetic elements in the modern metamaterial research, and from there the metamaterial research has gained momentum, right. So, the split ring resonator is a foundational magnetic meta-atom which is central to the artificial magnetism at microwave frequencies. So, understanding its development will basically start with examining a simple metallic plate in an oscillating electromagnetic field like this. So, you can think of a metallic plate where the magnetic field is basically perpendicular to it, and a circular current like this will get induced in the plate. Now, this current will basically generate a magnetic flux that opposes the external field, and that is described well by Lenz's law. Okay. So, that means this metallic plate behaves like a weakly diamagnetic material, right. Now, an array of such metallic plates can show an effective permeability just below 1. Now, the circular current in a metallic plate, you will see that mainly it is around the perimeter. So, you can safely remove the inner part and can create a metallic ring. Now, if you just think of the metallic ring alone, that is inductive, right, and it lacks a resonance. So, if you introduce a gap in this ring, that can introduce capacitance and you have L and C. So, you can enable resonance. Okay. So, as you can see in the figure, a gap in the metallic ring prevents the formation of a complete circular current, and charges will accumulate across the gap. So, you will get a capacitance here, right. So, the capacitance is effectively introduced. Okay. You can also put two rings next to each other. So, you can also introduce the mutual capacitance between the two, right. So, first you need to understand one element of how it is working. So, you can see that this inductance and capacitance make the split ring resonator work like a magnetic element. Now, when you bring another one, a concentric split ring, that can enhance the capacitance effect more effectively as compared to the split ring resonator, because here only this was contributing to the capacitance, but here when you have the induced current, you put it in the opposite direction. So, the current induced is in this direction, as this one is also in this direction. So, you can actually have this two giving you the mutual capacitance, and that can actually help you tune the resonance, and we will see that in the subsequent slides. So, let us consider this particular design, which is a double split ring resonator, that is nothing but a pair of rings that is considered as the meta atom. So, why a double split ring resonators are preferred? Because they minimize the electric polarizability, and they also reduce the effect of electric dipole, because there are two opposite dipoles created, and in that case the magnetic dipole moment will be able to dominate, right. So, that is why as standard double split ring resonator is mainly used as this metamaterial meta atom, not a single one, because once again in a single SRR, the cumulative charges you will see that will be around the gap, and that will give you a pronounced electric dipole moment, and that may overshadow the desired magnetic dipole moment. But when you put the two SRRs in this particular manner, what will happen? You have a dipole moment like this, you have a dipole moment in the opposite direction. So, they will basically cancel out each other, they will try to cancel out each other, and then the magnetic moment will dominate, and that is what you want, right. So, one thing it is important to remember, that the goal of the design is to create artificial magnetic atoms for a metamaterial. So, you have to ensure that the size of each split ring resonator should be much smaller than the free space wavelength. So, that is very important, that you have to ensure sub wavelength size to get the metamaterial behavior at target frequency range. Now, each split ring resonator acts like a quasi static LC circuit under the external field excitation. So, you can see that the ring structure basically provides the inductive element. You can estimate the inductance L as 2 mu naught R. R is basically the radius, inner radius of the ring. So, the capacitance basically arises both from the inter-ring slots, which is between the two split ring resonators, and also from the cuts in the individual rings. So, the effective current flow and the charge distribution, you can see that can create a complex path. So, you are having conductive and displacement current across both rings. Now, you have to see that the dominant capacitance basically arises between the two rings, because you have much larger length that is being covered, and the gap capacitance within each ring is basically much smaller compared to that. So, if you consider the total capacitance to be C naught, which can be approximated as 2 pi r epsilon naught 2 c by d. So, each ring is basically having width of c, d is basically the gap between the two rings. Okay. So, they cannot be directly used for resonance calculation though, because the total capacitance of the double split ring resonator is basically a series combination of the two separated capacitors. So, the effective capacitance will be like you can put C naught by 2 and C naught by 2. So, they are in series. So, the effective capacitance of this double split ring resonator is basically C naught by 4, right. And you can consider the ohmic losses because of the metallic, these are like metallic strips, right. So, the conductivity and the skin depth of the material, okay, will tell you about the resistance this guy is going to offer. So, you can estimate the resistance as pi r divided by C delta sigma. Delta is the skin depth and sigma is basically the metal conductivity. So, with that you get a equivalent circuit model of this double split ring resonator, and the full RLC circuit will give you the resonance frequency estimation. So, that comes out to be omega naught, which is square root of 1 by L plus R by j omega naught times C. So, this is a very simple model, but with this kind of LC circuit analogy, you can effectively estimate the resonance, and it also allows you to understand that how geometric parameters like C, then D, this is the gap, okay, the overall length which can be obtained from this radius, then you have C, then you have D, again you have C. So, all these parameters can tell you that how it is getting correlated with the resonance frequency. Now, the magnetic response strength and the effective permeability in an array of this kind of split ring resonators can be approximated using the magnetic moment of each unit. So, you can calculate mH magnetic moment as pi r square I. So, you can write this moment expression as mH can be also written as, in this case, pi square r to the power 4 mu naught h divided by omega naught square by omega square minus 1 times L. So, here you can see that H is basically the external magnetic field which is introducing the current, okay, I, and then the radius of the split ring resonator is considered to be R. L is basically the inductance, omega naught is the resonance frequency, and omega is the operating frequency, right. So, the effective permeability of the array mu effective can be estimated as 1 plus mH divided by Vh, where V is basically the unit cell volume. Now, the type of response, whether it is diamagnetic or paramagnetic, that depends on whether your omega is above or below the plasma, that resonance frequency, right, omega naught. So, here you can see that you are getting epsilon effective different from unity, even though the natural materials comprising the SRR array have unity permeability at the frequencies at about gigahertz or anything above. So, the constituent materials, they do not have any permeability, they have unit permeability, whereas the effective permeability from the structure, that is your mu effective, is different from unity. So, definitely this estimation is giving you something new, although it is ignoring some key behavior, something like electric coupling, bi-anisotropy and all these things. So, you can always do more accurate modeling using some kind of analytical and numerical methods which are already done extensively in the literature. Now, the split ring resonators designed in the gigahertz range were first implemented by Smith's group, I believe in Duke University, where the ring diameters were several millimeters length. Okay. So, double split resonators were first designed for microwave applications, which were commonly fabricated using printed circuit board technology. So, this kind of split ring resonators served as magnetic components in various microwave frequency metamaterial applications, and that enabled people to also demonstrate the first experimental realization of negative index metamaterial. So, you can make array of this kind of split ring resonators and couple it to the array of wire array. Okay. So, I believe we have already discussed those. So, if the wire array can give you negative permittivity and this array of split ring resonators can give you negative permeability, when you can have both permeability and permittivity negative over the same frequency range, you can get negative refractive index, right. So, this double split ring resonator marked the first explicit use of the term metamaterial in the literature, okay. And that is where from there the field of metamaterial just took off. Now, what is important to notice that after microwave range success of artificial magnetism, people working in the infrared and optical field, they also tried shifting this towards the infrared and the optical range. So, you have infrared and optical metamaterials. So, in that case what you have to do, theoretically when the frequency is going up, you have to scale down the split ring resonator design. So, that allows Maxwell's equation scalability, okay, frequency scaling you can say. Now, metals, they exhibit very different behavior in optical frequencies, especially they show +1 resonance. So, as compared to the microwave frequencies, right, when you there you do not have all those special effects coming in. So, simply downscaling of double split ring resonators will not work, because there will be some complexity and challenges also coming from the nanoscale fabrication, right. And as the split ring resonators size becomes smaller, you cannot even use the standard PCB printing method. So, you have to go for optical or e-beam lithography, right. So, people have done lithography fabrication of submicron metallic structures using layer by layer approach. So, split ring resonators need their plane to align with the incident wave vector for this effective magnetic field interaction. Okay. However, it is hard to accomplish when split ring resonators are basically lying flat on a substrate. One easy method to partially solve this issue is to use the oblique incidence for an external electromagnetic field. So, this will provide a magnetic field that obliquely penetrates the split ring resonator plane, and using scaling techniques along with inclined incidence, the resonance frequency of double split ring resonators have been pushed up to 1 gigahertz. So, here is the sample of terahertz split ring resonators with oblique incidence technique that is shown here. Okay. So, that was giving magnetic response in the terahertz regime, right. So, in this particular figure you can see the size, the dimensions of these elements are typically 40 micron, okay, and the resonance was and property was coming around I think 1 terahertz. Okay. Near the resonance frequency, the effective permeability shows a typical Lorentzian kind of spectral profile, and the permeability ranges from a minimum of -4 to a maximum of 4 at resonance. So, you are able to get both negative permeability at some particular frequencies, and you are also able to get permeability which is much larger than unity, okay, using this kind of a structure. So, with that we will stop here for this lecture. So, we will continue our discussion of optical magnetic elements in the next lecture, and you will see that how these elements can be used for making metamaterials working at higher frequencies. So, with that we will stop here. If you have got any query on this lecture, drop an email to this email address mentioning the course title and lecture number in the subject line. Thank you.